Hi again. So we're going to start now, and I'm going to go back and review the exam. Pardon me for being quiet. It's early in the morning. I want to wake up the household, which is my wife and the cats, and the dog is already up. So here we go. Where we left off, we had just finished talking about what goes on in the small intestine. Understand the small intestine has a lot of adaptations that facilitate its impressive role with absorption and digestion. So they have villi. Those are finger-like projections. Each one has a lymphatic vessel called a lacteal surrounded by a capillary bed. Millions of them everywhere. It has plica circularis so that the food goes down not in a straight line, but spirals its way nearly circularly throughout, pardon me, early in the morning, throughout the small bowel. And then finally, microvilli protrude all over that villus. The villus is about a centimeter. It's, like we're talking about barely a half an inch bump. And then it's surrounded by cells with microvilli, simple columnar cells that make it much easier to absorb. So that's really the critical, and it just creates tons and tons of surface areas we talked about before. The large intestine, on the other hand, doesn't do a lot. It's really there about absorbing water and sort of finalizing the consistency of what's going to pass. And it, at the most, some water, some electrolytes, maybe a few vitamins. That's about it that are really going to be done there. And the vitamins are facilitated by the bacteria that are there. Now, the interesting thing about it is it has anatomically, the large bowel has several anatomical interesting things. It's got tinea coli, which is really smooth muscle, but they call it the tendon of the colon. It holds its shape. It's got each of the large segments is called a haustrum, so collectively they're haustra. The first one is the cecum, and that's the one that the appendix protrudes from, pointing somewhat toward the umbilicus or the belly button. And then what you see after that are these epiploic appendages. And they're little like globules of fat. Don't know that they do anything, but they're just there. It's a way of identifying where you are anatomically. What's interesting about it is, and really it's a problem associated with aging, is over time, the walls weaken, and frequently older folks are subject to mechanical irritation. It just doesn't function quite as well as it should. They get polyps, little outpouchings, pushing in, and then they have weakness in the wall and they get outpouchings pushing out called diverticuli. And those can collect feces in them. They can get irritated. They can burst. They can get infected. They can really be dangerous. So that's something else to remember about. Really, so the small intestine is essential. The large intestine is not. The small intestine basically does everything: absorption and digestion, and the large intestine, can take care of what hasn't been taken care of, so to speak. There's just a little bit of functionality. Now, the interesting thing about what happens when we absorb something is it has to go to the liver to be processed. So, with the exception of some of the fatty and protein materials, because they're too heavy to fit, so to speak, into the small blood vessels in those little capillaries in the villi, they go through the lacteal. Everything else that's absorbed in the blood and the fluid of it, including bad guys and toxins and things like that, are brought to the liver. And that's the unique thing for it. Processes nutrients, it deals with toxins, it deals with materials that maybe shouldn't be there. There's a variety of things that it does. And the anatomical flow is it goes from the gastrointestinal tract by way of the hepatic portal vein, okay? And it does that way. So let me go back again. It goes from the intestinal tract, the GI tract, to the liver, and from the liver to the vena cava, the inferior vena cava, and then eventually back to the heart. That's usually the way it's supposed to go. That's there. So once it leaves the liver, so let's focus it this way. It goes through the hepatic portal vein to the liver, processes in the liver, collected by what are called the hepatic veins in the liver. They lead into the inferior vena cava, back to the heart, back to the lung, oxygen. And now you have processed blood now that's reoxygenated blood with the nutrients to go elsewhere to everybody else. Okay. And the liver does all of this stuff. It processes, it detoxifies, it makes the bile so you can break down fats. Okay. And that's its principal role. It doesn't produce a lot of hormones, nothing like renin for blood pressure or anything like that, not epinephrine or anything along those lines that are there. Now, the pancreas is different. The pancreas is basically a factory for enzymes and fluids that facilitate digestion and absorption. And they're almost all water soluble. So, and it's got to neutralize a lot of that acidity. So it makes a lot of water with bicarbonate. It makes a variety of agents that are able to uh, release proteins, trypsins and chymotrypsins and carboxypeptidases. All of those things are part of it. And a substantial amount of water as well are part of it. So that's something to remember about what the pancreas does. When you get to, that's most of digestive to focus on. Everything else is, once it gets into the large intestine, basically it's just finalizing it so we can excrete it, so we can expel it with bowel movements. So the major functionality of the pancreas is mostly an alkaline-based fluid to neutralize the acidity and a tremendous amount of enzymes, basically secreted as proenzymes, meaning inactive, that basically will break down everything from carbohydrates, nucleic acids, proteins. All of those kinds of things are going to be broken down, and it's even going to facilitate the absorption of fat. In the brush border, those microvilli, they have brush border enzymes. They're the final step. And what they do is they break down. So if it's a dipeptide, they break it down to single amino acids. If it's if it's a short chain carbohydrate like table sugar, it breaks it down into glucose and fructose. And basically, they're both absorbed because it's easy to convert to glucose. The big problem is lactose. So you have to have an enzyme called lactase. Some of us lack it. Babies generally don't have it. Then they develop it. And for some of us, it just doesn't develop either sufficiently or uh, sort of over the course of time changes, because a lot of people become much less tolerant to dairy products as they get older, and they notice it. I have quite a few in my family that are like that. They can still eat them, but some can't do it whatsoever. So that's just a little summary of digestion that's there. So, and again, the stomach very little stuff is quote unquote absorbed in the stomach, even though it's really undesirably when you have alcohol and non-steroidal anti-inflammatories and caffeine, and those are those we don't want to absorb at that point. Which brings us more to the kidney. And the kidney's job one, it's got a lot of them, is nitrogenous waste removal. That's because, and the reason I phrase it that way is that's the thing, when that starts to go off, when that starts to go in the wrong direction, we have a lot of tremendous problems. Our bodies just have very, very little tolerance for excessive nitrogen compounds. So they have to be removed. They're just inherently toxic and problematic. That's the way I phrase it that way. So the major problem is ammonia. And the thing, what happens with ammonia is that whenever we ingest proteins, and we ingest a lot, we basically, to process them, we have to take off the amino group. If you remember that from the chemistry part in AP1, basically, as soon as that's removed in water, it becomes ammonia. Ammonia is very toxic. So we take carbon dioxide, and with the carbon dioxide, we basically we alter it in such a way that we can take the oxygen, the carbon dioxide, and sort of magically convert it into something called urea. So that combination of carbon dioxide and a couple of ammonias is much, much less toxic, and typically the way we detoxify things, we make them more water soluble. So that's a big advantage with regard to that. So The kidneys work because they're a high pressure filter. The blood comes in much more powerfully based on its where it is from the heart. Generally, you get farther away from the heart, blood pressure goes down. The blood vessels, the arteries are quite wide. We looked at that anatomically. Those wide blood vessels make it relatively easy to get relatively high blood pressure, probably twice, slightly more than twice as much as it would into another capillary bed. What opposes it so it doesn't blow through the capillary bed is colloid osmotic pressure. That's the proteins in the blood that are pulling back the water from being pushed out by blood pressure. Blood pressure is pushing it out into the capillaries and out into that Bowman's capsule, and colloid osmotic pressure is pulling it back in. The fact that there's fluid in there also exerts a little pressure to push it back in. So you end up with that, but the net pressure is about 10 millimeters of mercury. So approximately the filtrate for most of us, okay, is quite substantial. It's about 180 liters, I would dare say. Between 160, probably 180 for men, about 160 for women, just based on size. And we absorb, we reclaim of this filtrate, which remember, filtrates all the water in the bloodstream, short of a little bit to keep whatever is left in there flowing, proteins and formed elements, red blood cells, white cells, and platelets. Everything else is filtrate, and we reclaim 99% of that, which means we generally excrete between 1 to 2 liters a day, depending on, let's say, how much hydration you have that are there. So what do we shouldn't see problems, and that's why that snapshot of your analysis, we look at blood, if that's in there, it's bad. We look at protein, that's bad. We look at sugar, that's bad. We look at ketones, that's bad. Those are all things that should not spill into the urine. Urine's going to have a certain amount of electrolytes. It's going to have some sodium, it's going to have some potassium, it's going to have some chloride, it's going to have some, obviously a substantial amount of urea, and they all create something, fancy term called specific gravity. It's a way of measuring how much solute is in it. You really don't have to. I'm not going to ask you about the specific gravity, but that's something we test frequently to give you an idea of if there's too much stuff coming out or not enough stuff coming out, so to speak. So most of the resorption of the solutes from the filtrate, in other words, all the stuff dissolved in a proximal convoluted tubule. Most of the secretion, proximal convoluted tubule. So 2/3 of everything that is eventually going to be reclaimed is pretty much reclaimed in the proximal convoluted tubule, including most of the stuff that you're going to put into the urine. The distal convoluted tubule certainly does more secretion than absorption, but proportionally much less. So the secret sauce is that proximal it doesn't make the distal convoluted tubule not necessary. It just makes it having, I hate to say, a lesser role. It's a different role. So to me, it's more about maybe some stuff will be reabsorbed. It's like the finalization of the product. Okay, went through the proximal convoluted tubule, reclaimed 2/3 of the material, even reclaiming some of the stuff we have to excrete later to create gradients or being able to flow with things. Then it goes through the loops, and the loops don't do a lot in the peritubular capillary beds, those cortical nephrons, but you get to those long loop juxtamedullary nephrons. That's where we finalize the water. That's where we concentrate, pulls water out, and to bounce it out, pull salts out. Okay, that's done. Now I get the distal convoluted tubule. In either of these, and it's let's do the final touches. Get rid of the stuff that we had to pull back in just to create gradients so we could pull stuff out and in and be ready to excrete it. That's the way I would look at it. So the water is in the thin segment of the nephron loop, and the salts that come out of the loop come out in the thick segment, the ascending. The descending is the thin segment. So again, the big players out are those juxtamedullary nephrons. And don't forget that juxtaglomerular apparatus is really an important player because that's that auto control, the elegant way it controls itself. And even sometimes when we're in fight or flight, it gets activated and it produces that chemical renin. And that renin is the catalyst for the renin angiotensin aldosterone mechanism. And that's a really big player. Remember that mechanism. The renin is released. The renin eventually activates the angiotensin, it's called angiotensinogen. Then it turns into angiotensin 1, which has some effect. And the lungs turn to angiotensin 2, which have a lot of effects. And those effects are to tighten blood vessel, tensing angio, raises blood pressure, make you thirsty, more fluid, raises blood pressure, secrete antidiuretic hormone from the hypothalamus, pulls back in water, more blood pressure, and releases aldosterone, the big player, from the adrenal glands. They insert those little sort of passageways, just like antidiuretic hormone, in the collecting ducts and the distal convoluted tubule, and therein comes additional water from the antidiuretic hormone. The aldosterone is the big player because it removes sodium and the water follows it. And so that's all really important. So you know all the effects of angiotensin 2. And so that's really the big player. The opposite, remember the anti-aldosterone is called atrial natriuretic peptide. We call it ANP. Okay, that's the one that comes from the heart, and that impacts blood pressure, but opposite. That sort of is, they call it the anti-aldosterone. So what it does is it tends to push sodium out back into the urine, not reclaim it. So it's opposite. And it's just sort of think of it, and the body has a ton of those mechanisms. Where it's that it's to a certain extent a little bit of negative feedback that goes on. Where if there's too much fluid, the heart senses it, says, get rid of a little more sodium because we're getting a little too much. And the big player in concentrating the urine, of course, is that countercurrent exchange, which is the countercurrent exchange and multiplier system. We just call it the countercurrent exchange system. The big problem, again, when it comes to diabetics is they if they're out of control, there's so much glucose it occupies all the transporters to bring it back. It exceeds what they call exceeding the transport maximum, and when it does, it spills over. That's the terminology in the urine. You can't reclaim it, and that's bad because that means that the maximum of the transporters are being used, and the more that we work at maximum, the harder it gets. Effectively, it lowers the maximum. So effectively, it's a vicious cycle. The more you occupy it, the more sugar comes out. But the more that it's occupied, the less able they are to do their job. And so it effectively, unless you keep it well below the transport maximum, that's sort of, again, part of the secret. So we find urine because it can't be pulled back in the bloodstream as it exceeds the transport maximum, and that's a problem. Aldosterone's all about sodium. Don't forget that. Antidiuretic hormone is all about water. Its name tells you exactly what it is. So in general, then when we get into the passageways that are there, effectively not a lot of activity goes on in the urinary tract unless it's bad, would be the best way to describe it. The ureters are there, they're hollow tubes, they're wide enough for fluid to pass. I mean, they expand rather easily. It's all about the transitional epithelium that we find there and in the bladder. The big muscle is the detrusor that surrounds the bladder. Again, if you get this wrong, you're crazy. You aren't listening to me. When we see visible blood called frank hematuria, in other words, blood where you're peeing red, it's a strong possibility of bladder cancer. Look at me. Okay. Women are much more likely to have bladder infections, and we're not talking, it's anatomical. It's basically the short urethra. And the big problem again with diabetes is diabetes has an autoimmune component, and that autoimmune component in a fair amount of diabetes begins to put lumps of protein into the glomeruli, and they don't work, and the kidney begins to fail. So it's the most important cause for kidney transplants and people on dialysis by far and away is diabetes. Then something called systemic lupus erythematosus, which is an autoimmune disease different than diabetes, and it produces those similar kinds of clumps. And most of the time, when you have kidney stones, and kidney stones have a lot of causes that are there. I personally think calcium is the most important one of those, but blood, bacteria, are the nidus or the core of it. but they're mostly in the ureters. You can get bladder stones, but they're not necessarily as big of a problem. They may have to be removed, but they're not necessarily as immediately big of a problem as kidney stones, certainly from the standpoint of pain. And I'll take a little break here, and then everything else that we're going to be going over is repro. I know we haven't done the repro yet, so I'm going to hold off until we at least get started with that in lecture. Because the repro is a pretty substantial point of that. I'm trying to make it so that the part that's the freshest in your mind is the part that we're focusing on in the final, and that's the reproductive. So thanks a lot. Hope you could hear this. I was talking in a whisper. Bye-bye.